जी हाँ वो इशू ये था कि लास्ट वीक after Thursday's lecture I was quite sick. I had food poisoning, so I couldn't do anything. So I'm gonna upload all those previous things today, and I have also written some homeworks which I wanted to share yesterday, but I'll share them today. And I couldn't do the tutorial on Saturday, so I'll upload a tutorial tomorrow, and then there will be a tutorial recorded on Saturday. So those two tutorials will help you with the homeworks. So I'm going to send an email about all of this. Okay, so what we're going to discuss today is the row and column spaces of a matrix and some theorems related to them. So we started doing this last time. And what was the row space? So you have a matrix. We know that it's composed of some rows. So you have a, let's say, M by N matrix. So it has M rows. And each row has, because it has N columns, N components. So you just take the rows and make a span. Make a span of row vectors. So since we know that the span of any number of vectors always gives you a subspace, so this is going to be a subspace of where they live. So where do they live? These are n component row vectors. So Rn, but since we are not writing them as column but as rows, so I can just put a tilde to denote that. Similarly, I'll have column space. So this was the row space. And column space is same, take n columns, all the columns, and span. So again, it's going to give you a subspace. Each column has m components, right over here. If you look over here, has m components. So it's going to be a subspace because they live in Rm. So this gives you a subspace of Rm. And related to row space, we define the rank, which is just the dimension of the row space. Then we also prove this, or argued it. It's very simple, that two matrices that are row equivalent, they have same row space. So you are not going, when you go from one matrix to another by row operations, you're just making more linear combinations of the rows. So that doesn't take you out of the row space. Now let's look at how to find the rank. Rank of a matrix. So that's the first issue today. So what you can do is you have a matrix A. You just go to its Ashland form. Yeah, I have written over here, dimension of the row space. So you take the rows, span, you'll get a subspace of Rn. Now that subspace could be Rn itself, or it could be a smaller space. So whatever the dimension of that smaller space is, that would be the rank. So I'm given a matrix and I want to find the rank. So what I will do is first go to the Ashland form. So how does an Ashland form usually looks like? You have things like this. You have a lead variable. Then in the next column, you have another lead. Then it's possible that in the next row, so in each row you have a lead variable, but what can happen is you can, for example, skip and go here. But if this happens, you will have all the zeros down here, but some other entries here. This is just one example, like typically what you get in the Ashland form. So, but what happens is in each of the successive row, you have some extra zeros. Now, if I have two vectors, so this property that each successive row has extra zeros. This says something about their linear independence of these vectors. So let me let's see what does it say. So first of all, if I have a vector like this, these are row vectors, but I'm just writing the column. The argument is exactly same. I can take these rows and put them as columns because I want to just do it in general. If you have this vector and then something like this, sorry. Can you please turn off your mic? Someone's mic is open. One and some entries. But in the rest of them, in the first one, you have, in this one, you have an extra zero. Over here, you have two extra zeros, and so on. In each successive one, you have more zeros. Now, if you have this kind of property, and if you check the linear independence, so you make something like this. This one could even have more zeros. Now what happens is that if I look at the first entry, I have to match the zeros on both sides. This can only happen because the first entry only in the first column is non-zero. So this will require for me that C1 is 0. Similarly, if C1 has been put equal to 0, the second entry in the second vector is non-zero, but in the rest of them, the second entries are 0. So I have already put C1 equal to 0. And I want to somehow make the zeros by combining the rest in the second entry. So the only option is that the C2 is 0 and then C3 is 0, because C3, where you have found the 0, you have to then, you cannot cancel it against some entry from C4. So these are the only options you have. So that means if you have like these successive extra zeros, then these vectors are linearly independent. Because that's the only way you can make a zero out of them. If you have, just for fun, let me take another example. Well, let's just stop here. So these are linearly independent. So the same thing is happening for your row vectors. Like over here, if I go to the next one, so all these entries below it are 0. I have to combine these rows with some constants and make this row. But since all the entries below the first row are 0, whatever C2, C3, C4, C5 I choose, I'm still not be able to cancel anything with the C1. So I will have to put C1 equal to 0. Similarly, put C2 equal to 0 to make the second entry equal to 0, and so on. So that means that all the vectors, if I look at, consider all rows with a leading 0, they will be linearly independent in any row echelon form. But then you can have some completely 0 rows. So now I know that all the rows generate or span the row space, and on top, all the rows with leading ones are linearly independent. But then I have some extra rows. They will be in general some completely 0 rows. But those completely 0 rows don't matter. Those are just 0 vectors. They do not show up in your span. In your span, if you add another 0 vector, you multiply it with any constant and add it to your rest of the vectors. It doesn't do anything to that vector. And they do not spoil the linear independence of the rest of the vectors. So they pretty much do not matter at all. So if I have these vectors, up to CK, up to VK, and I'm spanning some space. And I know also that if I put them equal to 0, this implies that all these CIs are 0. Now if I add to them a couple of zeros, 0 vectors, with some constant, any constant I like, this does not change the vector. This is still equal to the original vector I started with. So the span is not changed if I add zeros. And when I check the linear independence, these zeros do not matter. I never consider these zero vectors in checking the linear independence. So you just take them out. So that means that the row space, its basis is the non-zero rows in the Ashland form. So that simply means that the rank, and since they are, so that's the basis. So dimension is just number of elements in the basis, number of vectors in the basis. So rank of A is just, because it was the dimension of the row space, is the number of non-zero rows in the Ashland form of your matrix. We will shortly do some examples as well. But now we can make some statements based on these row spaces and column spaces. Some statements about solutions of linear equations. So first you have a statement about consistency. So I know that I can write a linear system in this form, right? Where A is m by n, x is a n column vector, and so is, and B is a m column vector. So this will be consistent if B is in the column space of A. So what does that mean? So I have this equation and I'm considering the column space. So I write the matrix as these bunch of column vectors. How many you have? If it's a m by n, so you have n columns, each having m components. So I know that this matrix product, this product of matrix with the vector, we have now done it so many times, is just this linear combination. Take the components in X and make linear combination with the columns. So that is equal to B. That's what this equation A is saying. So, but this linear combination, this lives in the column space, right? Because this is just a span of the column. It's in the span of the column. So that means B is just this vector. It lives in the column space. So if B is column space of A is a subspace of M. So if B is in that subspace, then your equation will be consistent. Otherwise, it will not be consistent. So it's kind of an obvious statement, but it gives you also some kind of a geometric picture. So for example, if I consider 3 equations in 2 unknowns, so I can write them so I'm taking an example equation. Just randomly. So you have 2x1 plus x2 is equal to 1, 3x1 minus x2 is equal to 1, x1 plus x2 is equal to 3. So this can be written like this. And that has to be equal to this. So now what you have, I can consider I have like a 3-column vector. So in this special case, I can draw this first vector. Let's call it A1. This is A2, and this is B. I have this A1 in 3 dimension. I can translate it into a 3-dimensional vector, and an A2, it will be pointing in some other direction. But 2 vectors, they form a plane, and their span would be all the vectors in that plane. Now, if I randomly choose a third vector B, it may not be in that plane. But typically, if I randomly choose a vector B, it will be outside the plane. So it will not be in that subspace. So that is why if I generally take 3 equations in 2 variables, it's an over-constrained system, and there's a very big chance that my system will be inconsistent. Unless if I choose B in a special way, how do I choose? I choose it in the same plane as in the plane formed by these 2 columns. So that's why over-constrained systems, they have a very big chance of being inconsistent, because you are considering a subspace and your right-hand side must be lying in that subspace. If it's not in that subspace, you will be inconsistent. But if I, for example, another example, if I consider 3 by 3 system, then I will have x1 some column plus x2. Now I have 3 column vectors and 3 unknowns, because it's 3 by 3, and I'm making a 3-component vector. Now, if these guys are linearly independent, if all 3 are linearly independent, all 3 column vectors of your matrix A are linearly independent, then they will form a basis of R3. So then over here, you can put any B, and you will be able to make that by using a linear combination of these basis vectors. So you will be very easily able to find these 3 numbers which makes up any B. However, if they are not linearly independent, then we know that we can get rid of one of them. And for example, I can then come down to 2. So again, I will have a subspace, 2-dimensional subspace, and then I will not be able to write any arbitrary B in terms of those. But if I choose in random 3-column vectors, usually there's a big chance that they will not lie in one plane. So a randomly chosen 3 by 3 system will have a very big chance of being consistent. But still, you can have situations where they're not linearly independent. So in those special situations, you can end up with an inconsistent system, but not that often. On the other hand, if I throw in another vector, I'm only increasing another vector. So more variables, less equations. I'm providing more vectors. I'm only increasing a chance of picking up 3 of them, which are linearly independent, or a combination of them which are linearly independent. So you will be able to find a basis. It's a bigger chance that these all 5 do not lie in a smaller dimensional subspace. So then you're just increasing your chances of having the system consistent. And this is what we learned in the beginning of the course, that if you have more equations than the unknowns, there's a very big chance that the system can be inconsistent, but it can still be consistent. If you have same number of equations as the variables, you have a bigger chance of being consistent. And if you have more variables and less equations, then it's much more likely to be consistent. So this discussion, we can kind of summarize in this theorem. An m by n system like this is consistent for any b if the columns of A span Rm. That is the full space. So B's live in Rm, and if the columns span, you don't not need them to be linearly independent. If they span the full, so like if I have these 5, then I know that the basis of R3 only has 3. So if I put in extra, I can still span. It's just that they're not linearly independent. I'm doing more than required. But if you have a span, you have a span. You can make any vector. If you have a spanning set, you can make any vector out of them. So if you have, if you want your system to be consistent for any B, then the column vectors of A better be the spanning set of Rm. It's kind of obvious. So proof is obvious. We can also discuss uniqueness of the solutions. As a unique solution, if columns of A are linearly independent. So you pick a particular B has a unique solution if it exists if columns of A are linearly independent. So we are assuming that this equation has solution, it's consistent. If it's consistent, it will have a unique solution if columns of A are linearly independent. So from existence, that the solution exists, we know that the B has to be in the column space. So B must be of this form. Some numbers, so solution number. So solution I am writing as a tilde. This is just our previous statement. It has to be in the subspace spanned by the columns. Now, instead of tilde, let me write C1 for the clarity. There will be some solution. There will be a linear combination of the column vectors, B's. Now you have, from this equation, I have from this equation, x1, a1. So let's say, suppose there's another solution. D1, and that is also B, has to be B. So X is equal to C, this is one solution, and X is equal to D, one solution, and this is the second solution. So I can subtract these two equations, and that will give me A2, AN is equal to 0. But now, since these column vectors were assumed to be linearly independent, these guys are linearly independent. So that means all these coefficients must be 0. So that means C1 is equal to D1 and so on. So these two vectors are same. So there are no two solutions. There's only one solution if they are if the columns are linearly independent. So that's a very easy way to check. If the columns are linearly independent and a solution exists, the solution has to be unique. There is a corollary for this. Well, I can change this theorem a little bit. If B has unique solutions for all B, AX equal B has unique solutions for all B if and only if the columns vectors of A are linearly independent. So one side we have shown. The other can be shown also very easily, that if the solution is unique, then you can very easily show that the column vectors are uh, are linearly independent. So since I have written that the unique solutions for all B, so suppose take B is equal to 0, then AX is equal to 0 should have a unique solution. What is this equation? This equation is just a linear combination of the columns. And it must have a unique solution. And I know that the unique solution for a homogeneous system is always that all the xi's are 0. So that means this is 0 only if all the xi are 0. But that is telling me that these columns are independent, are linearly independent. So you can draw a result actually that if is consistent for all B and has unique solutions. So B is living in R M and has unique solutions. So that means all the columns are linearly independent and they generate. How many columns you have? We have n columns and they are linearly, they generate, they span Rm because it's consistent for all of B. But since the solutions are unique, so they are also linearly independent. But I know that if M is less than N, so I have less vectors than the dimension of this space. So if N is less than M, that means I have less vectors than the dimension of the space which I am spanning. I cannot just do it. Less than n vectors, less than m vectors cannot generate the space. So I have to have at least n is equal to m or more than m. But I also know that if I have an m-dimensional space and I consider more than m vectors, they will never be linearly independent. In a m-dimensional space, m plus any number of vectors are not linearly independent. So that means this situation will only arise if n is equal to m. And actually, then the columns form a basis because they are linearly independent and they generate the full space. So they are a basis. Another interesting result you can draw an n by n matrix is non-singular. So you can check if it has an inverse or not, if and only if column vectors of A form a basis. You can write it in this way, or you can say if and only if they are linearly independent. Because we know that if in Rn, if n vectors are linearly independent, they already form a basis. So they are interchangeable statements. Form a basis of Rn. So it's an n by n matrix, so these columns live in Rn. So how do I prove this? So choose b is equal to 0. Then this thing has a unique solution. Well, actually, even if you don't choose b equal to 0, we know that these equations has a unique solution. We have done it before. If and only if a is non-singular. If a has an inverse. But we just saw, but a unique solution exists if and only if columns are linearly independent. So you can translate this statement to this statement and connect them. So that just implies that you have A is non-singular if and only if columns of A are linearly independent. Yeah. So you check the non-singularity, and there's another way of making determinants. So you can tell if a determinant is 0. You know that determinant, when determinant is 0, then you do not have the inverse. So I can, for example, if I write this matrix, what is the determinant? I don't have to compute. I can just directly tell. Because I have two vectors which are same. So that means these are not linearly independent. I can cancel the first against the second and put the coefficient in front of the third as 0. Choose the coefficient of the first as 1, of the second as -1, and third as 0. You do not have all the coefficient equal to 0, but you are still making a 0. So that means these guys are not linearly independent. That means they cannot have an inverse. This matrix cannot have an inverse. So its determinant has to be 0. So that's why whenever you have two rows, two columns same in a matrix, its determinant is 0. Or for example, if I take this guy and I add 2 times the second to first uh, and create this row. So -2 plus 2, 0, 4 plus 1, 5. Yeah. So if I look at this matrix, it's not very obvious. But if you could unentangle and just notice that the third row is 2 times the second plus the first. So the third vector is a combination of the first two. And we know that when this happens, that means they're not independent. They're not linearly independent. I can make a 0 out of them. So this has to be 0. And so on. And also, since we know the determinant of A is equal to determinant of A transpose. So the same statements hold if instead of 2 rows, 2 columns are same, or if 2 columns are linear combinations of each other. Now let's come back to this concept. I think I didn't use this name before, but we discussed the null spaces. So nullity is just the dimension of the null space. What was the null space? You have a matrix. You consider this equation. I'm not claiming that I have unique solutions here. You consider we proved that if I consider all the vectors x, all the solutions of this equation, they will form a subspace. So I'm just counting the dimension of that subspace. That would be nullity. So how can I find the dimension of the null space? You can go to reduced Ashland form to find the dimension of null space. So we know that if I do row operations, the solutions do not change. The solutions of these equations are exactly same. They are one-to-one map between solutions of, if I go to the reduced echelon form, because row operations do not change the solutions. So whatever is the null space computed from here would be same as the null space of this. So I can just go to the row echelon form, reduced row echelon form, and from there it will be easier to pick up what is the null space. Now, how would the row echelon form, reduced row echelon form look like? You will have a leading zero. So just as an example, and in the next row, you have to slide 1 or 2, whatever, so suppose. And in the reduced one, you have a 0 up as well. In the next one, it's possible that I have to slide by 1 more. These are not guaranteed, they can be non-zero. Well, yeah. And then I have, suppose, zeros here. So I'm just writing a kind of a general form for reduced echelon forms, what kind of things you can get. You have lead ones, but they can be slided by more than, so instead of dropping by 1, you can draw, you may have to slide and then drop. And you can have complete zeros in the at the bottom of the matrix. That's how we defined the reduced echelon form. And above and below the leading ones, you have to have zeros. The others, they are not guaranteed. They can be something non-zero there. So this I'm putting equal to the zero vector. Now you have leading ones, number of leading ones. This is, we know that this is equal to number of what we were calling lead variables. So like over here, I have something like x3, x4, 5 variables in this example. Let's call it R. So how many then you have the free variables? Free variables, if you have an m by n system means you have total n variables, is n minus r, right? You just subtract the lead variables, the rest are free. And all the possible solutions, they look like this. So you know that the free variables, you just put them equal to something free, any number. So like in this case, which ones are free? Wherever you don't see a lead in the column, that's a free variable. So x3 is free, I can put alpha. Similarly, x5 is free, so I can put a beta. And the rest in the row echelon form are easy to read. This is something like A alpha plus B beta. For the x2, again I will have C alpha plus D beta. And for x4, since it's over here, it will have just the beta. Some other cone A, B, C, D, let's say E beta. But the point is that the free variables, they are completely free, and the rest are linear combinations, fixed linear combinations of free variables. This A, B, C, D, E are fixed in your matrix, whatever form you got. Alpha, beta are free. So your solution, general solution will look like C, D beta, alpha, E beta, beta. Now I can separate alpha and beta. Zero, and I have a E here and 1 here. So now I have got my subspace because I have these two fixed vectors which are being spanned with arbitrary alpha and beta to give me my subspace, which is the null space. Now my claim is that these vectors, these fixed vectors, will always be linearly independent once I make them out of the reduced row echelon form. Why? Well, because for the free variables, what do I have? I have a linear combination of these kind of free variables in general, so on. And when I separate out these alpha ones, I will have one at a particular spot. So for example, if it's the third variable which is free, I will have a 1 at the third spot. And in the rest of them, I will always have a 0. And then, for example, I have sixth variable as free. So I will have a 1 corresponding to this alpha 2, if alpha 2 is for the sixth variable. And 0, I will put zeros at the other spots. So we just saw at the beginning, if we have this kind of a situation, that on a one particular spot, like the ith component, only in one vector is 1 and in the rest is 0. And same is true for the other components. Then these cannot be linearly dependent. They have to be linearly independent. Because for example, if in this example, if I put it equal to 0, this 1 cannot be cancelled against anything over here. You have a 0 on the other side. So you have to put alpha equal to 0. Similarly, this 1 cannot be cancelled with anything against this. So you have to put beta equal to 0. Similarly over here, This one cannot be cancelled against anything, so I have to put alpha 1, 0. But this guy has nothing, no component, corresponding component in the other vectors. So you have to put alpha 2 equals 0. So all the alphas turn out to be 0. And in the reduced echelon form, these vectors which span your null space will all be linearly independent. So how many these fixed vectors you have? They are exactly equal to the number of free variables. So the conclusion is that the dimension, you have to go back and think about it. I know it was kind of fast. Is exactly equal to number of free variables. And this number of free variables, I think we called it R. Yeah. No, we didn't call it R. Yeah, we called it n minus R. So this is the nullity. And we wrote this equation that n minus R is equal to number of free variables. So n minus R is equal to the nullity. But what is R? Lead variables, but is equal to something else. Because leading ones is equal to the number of non-zero rows, right? Each leading one will lead to non-zero rows, and the rest of the rows will be zero rows. This was the leading number of ones, but this is equal to number of non-zero rows. Because at each point, you slide by one or more than one. So if you collect all the leading ones, the rest you will have to adjust by having completely zero rows. So this is equal to number of non-zeros. We just in the beginning of the class we said that that would be equal to the rank of A. So that means from this equation, n is equal to rank plus nullity, or n is equal to dimension of row space plus dimension of null space. It's kind of very neat result. Let's look at an example. So I'm not gonna solve it, but directly write the row echelon form, the reduced row echelon form. So it's a 3 by 4, and it is this number, the second number, which comes in that theorem. So what's the rank? Let's call it A. What's the rank of A? Number of non-zero rows in this reduced echelon form. So you have 2. And what's the nullity? Is the number of free variables, free leading, or in other words, number of leading number of free variables, which is in this case how many you have, this column and this column. Nullity is 2. So 2 plus 2 is equal to 4, which was this number. Let me do we haven't done this thing in a long while. Let's do a complete example. Wait, do I need to do anything over here? No. Let's first do this, then I'll do the last result. So I want to find the I think it will be better if I do, because I want to, using this example, I want to discuss a few things. So let me reserve this example for now and first prove this theorem, which will have many other revealing things as we go through this proof. So the theorem says dimension of row space is actually equal to the dimension of column space. So like you may have like 3 rows and 7 columns. And if those 3 rows are linearly independent, you know that the dimension of the row space is 3. But those then 7 columns somehow cannot be linearly independent. Well, we know that if it's a 3-row matrix, then those 7 columns are 3-component objects. So they cannot have more than 3 linearly independent vectors anyway. But suppose if these 3 rows themselves are not linearly independent, out of this, the dimension of this subspace is 2, then you are automatically guaranteed that the column space will also have somehow dimension 2. It won't have like, when you generate it, you won't have 3, you will have only 2, and so on. So if I'm given a matrix A and I go to its echelon form, something like this. I'm just considering the echelon form for now. Don't need to go to, you can, if you want, you can go to reduce echelon, but echelon is fine for this logic. So I know that these non-zero rows are linearly independent in this case, because in each next row you have an extra zero which cannot be matched up. So like over here, this one cannot be cancelled by anything below it. This one cannot be cancelled by anything below it, and so on. But what about the columns? This guy and this guy I find, so you have a zero. This one, you do not have zeros over here. And if you look at this one, this has 0, 2 0. This has 3 zeros below it. This has 2 0 below, two zeros below it. But this guy also has 2 zeros below it. So like this one cannot be cancelled against anything to the left. But what about this one? This can be cancelled. There are things around over here. So what is causing the problem is this. If this guy was not here, I will be having something like this. Now I can use the same logic starting from this number 1. Cannot be cancelled against this, so the coefficient of this guy has to be 0. But if the coefficient of this is 0, then these two have to be cancelled among themselves. So this one then cannot be cancelled against this 0. The coefficient of this has to be 0. Then so on. Then this guy, if this has to become 0, so I then need C1 equal to 0. This logic was failing here because it's true that C4 had to be put equal to 0 because I cannot cancel this one against any one of these. But C3 and C2 could cancel against each other, right? Because I have an entry here and an entry here. Because you have these successive, in the previous case, you were having successive cases, zeros going as you go, successive zeros below as you move through the list of vectors. Here you have successive zeros going up as you move through the list of vectors. Or you could have even gone to reduced echelon form. Well, this reduced echelon form. And then it will look like this is like that. So now it's much more easier to see that this one cannot be cancelled. This one, the one in the first column cannot be cancelled against those things if I put this C4 equal to 0. But these guys can cancel, these ones. And also because of the C3, C1 can be cancelled. But if I delete this row, which does not have the leading one, that column which does not have the leading one, then I'll have this thing. And now because each column has only one and not at the same place as the other columns, right? So now I will not be able to cancel anything against each other. So these will be linearly independent now. So when you go to the echelon form or reduced echelon form, the rows, non-zero rows are automatically linearly independent, but not the columns. Columns are not automatically linearly independent in general, but if you delete those columns which do not have a leading one, then you end up with linearly independent columns. So delete, go to reduced echelon form and delete columns that are not leading, that do not have leading one. The rest would be linearly independent. So I delete those columns in the reduced echelon form, and the corresponding column I delete in the original matrix A, and I denote these guys by tilde. So this is something like this. And correspondingly, I will have A tilde, which will also be a 3 by 3 now, a 4 by 3 now, because I deleted one column. So I delete as many columns I delete in the reduced echelon form as I delete the same columns in the original matrix. But you can note that these new matrices are still related by row operations. Why? Because I went from A to the reduced or echelon form through row operations. If I just leave out one column, the rest of the columns are not affected. They are changed by these row operations. So the same row operations take me from A tilde to A tilde echelon. Now, because they are related to row operations, that means this equation implies this equation. They have same solutions, row or echelon doesn't matter. And they are true. This thing is true if and only if, because all the columns are linearly independent, and we know that if all the columns are linearly independent, this will be true if and only if you have a unique solution. Or just because they are linearly independent, so I know that this equation is satisfied only when the coefficients are 0. But this implies, because they have same solution, exactly same solution, this implies 0 only if, actually if and only if x is 0. But I know this happens, but this happens, we proved above, only if the columns of A are linearly independent. So what's the conclusion? The conclusion is that the dimension of the column space. So we haven't really found the dimension of the column space. We just know that if I delete those columns which do not have the leading ones, the rest are linearly independent. That means the dimension of the column space is at least equal to those remaining columns. So that means dimension of column space is bigger than or equal to the rank, because number of leading ones is also equal to the dimension of row space, its rank. So the dimension of column space is greater than or equal to dimension of the row space. Let's call it 1. because leading ones give you the dimension of row space. And we know that if you collect the leading one, columns containing leading one, they will all be linearly independent. But there may be extra columns and we don't know if they are linearly independent with them or not. So the dimension is at least equal to the dimension of row space, could be more. But now I do a trick. I write dimension of row space of A is equal to, obviously, column space of AT transpose. Because if I do the transpose, those are replaced by the columns. But from here, for this guy, I know I now use this result. Is equal to dimension of row space of AT. Now I again use a result. I again bring it here. Dimension of row space of AT is equal to dimension of column space. Again, replace rows by column of A. So this is equal to this, and this is greater than this, which is equal to this. So I have proved dimension of row space of A is bigger than equal to dimension of column space of A. Right? Because dimension of row space of A is bigger than dimension of row space of AT. But dimension of row space of AT is equal to dimension of column space of A. So this is 2. And one said the opposite of it. One said that the dimension of column space of A is bigger than or equal to dimension of row space of A. So only possible if dimension of row is same as dimension of column. So very interesting theorem. I've run out of time, so I think I'll do this example in the one of the tutorials.